Right. So yesterday I was saying that I want to explain how to prove this divisibility. And so I set up some notation to explain the ideas. So let me just remind you what we are doing. So like I said, these objects are objects over the F infinity, like the whole tower of my extension. And we will try to project things to finite levels. So I will project to F, which is Fm. So it's the nth layer of my extension. A is the Galois group of Lm over Fm, which will give me y infinity co-invariant by gamma m. And pi will be the Galois group of F over Q. So this is the finite extension over Q. R will be the group ring of this Galois group pi with coefficients in Zp. And so I have a natural projection from my Iwasawa algebra to this group ring. And so remember, beta is this generator that gives me this quotient. And then Q is a finite lambda module in this short exact sequence. So I'm interested in y infinity. So y infinity sits inside this short exact sequence. So we have some cyclic module quotient out by this Fi, and then we have the finite module here. So I fix the ionator delta for this finite module. And so I fix some power. So this is power of P. So S is a power of P that ionates both of these two modules, these two quotients. And then I fix this power of P given by this large product. Furthermore, I want to project things modulo this P power as well. So, so T will be this P power. And I'm looking at this curly R, which is this group ring of pi with coefficient in Z modulo T. And then we will eventually let m goes to infinity. And then when m goes to infinity, then I will get the lambda divisibility. And so just another piece of notation is that, so we have, I'm sorry. So we have another projection map that I can define from my USR algebra to this group rank with coefficients modulo T, and I'll write this projection map as star. X will be sent to X star. And so the theorem is that for I between 1 and R, so this R, this small r, is the R in this short exact sequence. So remember, I have R cyclic module here. So for each of these I between 1 and R, we have the divisibility F1 multiplied up to Fi star. So we project this product into this finite group ring. It will divide gamma minus 1 times beta times delta to the I plus 1 of this project to this finite group ring. So remember what is gamma? Gamma was, so I'm sorry, I'm going forth and back because I want to remind you the notation that I introduced yesterday. So gamma was the topological generator of the ZP part of my Galois group. So in other words, gamma 1 is just X. So this is this variable in my power series ring. So so we will have this theorem. And so this does not precisely give what I am looking for, because we want to show that the product of Fi divi is beta. So we have this actual factor, which we can actually get rid of. I will explain briefly how it goes. So the point is that here, like I said, as m goes to infinity, we get the divisibility in lambda. And so the point is that, so in particular, if you take I equals to R, then you get this divisibility. So first of all, this delta I can actually get rid of. So the point is that delta was what? I remind you, delta is an alienator of Q, and Q is a finite module. So in some Iwasawa theory jargon, this is a pseudo-null module. So Q is a pseudo-null module, meaning that it is supported at some height 2 primes. So in fact, what we can show is that we can, so since Q is a pseudo-null lambda module, we can actually find two different deltas. So let's say delta 1 and delta 2 that are co-prime. So in other words, this choice of delta, I can choose two different choices of delta that give me the same divisibility. And so sorry. So once you have that, then so you have F1 times up to FR divides both these two terms. And so since they are co-prime, so just by some simple algebra argument, then you know that you can get rid of them. So and then to get rid of this gamma minus 1, you can show that using some control theorem again, you can show that which tells you that when you go from y infinity to ground level, you know that it gives you something finite because it gives you the Galois group of y0 over f0, and so so if you have a lambda module such that when you take the gamma covariant is finite, it would correspond to looking at whether this is divisible by this. So when it is finite, it would tell me that it is not divisible by this term. So that tells me that the characteristic ideal of y infinity is co-prime to gamma minus 1. So all in all, these terms are not so important in the end. We can get rid of them. Yeah, so the idea of the proof is by induction. The proof is by induction on I, and we will require, we will make use of a filtration on A's, so which is something like this. So can actually filter A using slick kick R modules. So this is a kind of technical result which I won't explain. These are all in the book of Coase and Sujata that I mentioned yesterday. So if you want to see the details, you will be in there. So I'll give this exact sequence a name double star. So this is a finite module that so yeah, this is queued by my choice of delta. So this Fi is precisely the Fi we had in the other short exact sequence earlier, and this is a cyclic R module. Yeah, so you have this. Yeah, you can somehow chop up your A this way, and then each graded piece will be related to this cyclic quotient up to this finite, but which is Q by this delta. So in other words, you can somehow approximate your A piece by piece with these quotients. So now to prove this theorem 1.7, we will then make use of an Euler system argument. So we haven't talked about what an Euler system is, but I just want to mention to you how the argument works. And then once you have seen this argument in action, then I will tell you what is the formal definition of an Euler system, and then that will maybe make more sense why we define an Euler system this way. Okay, so yeah, so to explain this, I have to fix some more notation. So so we fix integers, which are k, which is at least 2, and then I have some other integers going from a1 to ak, which are non-zero, and also n1 up to nk, such that the sum of these integers is 0. And then I'll define this alpha t, which is given by this product with respect to these integers that I have chosen. So this is a function in t like this, and so okay, and then I fix S to be a set of primes that includes 2 and also the primes that divide this product of AI. So I'm looking at all the product with all the primes in the product of this AI. So this, okay, so why am I defining this funny function? So you might notice that this t to the ai over 2 and t to the minus ai over 2, it resembles a little bit of what we saw in the definition of the cyclotomic units. And indeed, when you plug in t to be a d root of unity, then it gives you a cyclotomic unit. Okay, so you can recover the cyclotomic unit using this function, so once you have noticed that, you then realize that this function satisfies some kind of norm relation, which I will just write down. It resembles the norm relation that we saw yesterday. So if d is an integer that is co-prime to s, and q prime such that q does not q is co-prime to d and s, and then for a root of for d root of unity and a q root of unity, which is not 1, we have the following norm relation. So when you take the norm from the dq cyclotomic extension, and I take the totally real part like this. So like I said, when you apply alpha to this product, so this product will now be a cyclotomic unit in over dq, and then it will give you a cyclotomic unit over say the d, and just like before, we will have some Euler factor like this. Yeah, so it is essentially a very similar calculation as the one we did. We saw yesterday. Okay, so yeah, this function gives me some cyclotomic units, and these cyclotomic units satisfy the some kind of norm relation. Okay, and now I want to introduce more notation in order to explain some of the ideas behind the proof of that theorem. Okay, so ZS will be the set of square-free integers which are prime to S and P, and ZS1 will be the set of square-free integers such that these products will be 1 mod T. So remember this mod T was that power of P that we fixed earlier. So it is this T that we have fixed earlier. And then I want to look at some extension of F. So for positive integer n, we write Jn to be the extension of F given by zeta n, and again I take the real part, and I write delta n to be the Galois group of this extension. Okay, and if Q is one of these prime in ZS, meaning that it's prime to S and P, then the Galois group delta Q is cyclic of order Q minus 1. So I can fix a generator for this Galois extension. So let's call this tau Q. And then once we fix a generator of this group, then we define the Kolyvagin derivative, which is given by dq, and it is a sum that looks like this. Right, so it is like this, and then so this is what? This is an element in the group ring of delta Q. And similarly, when I have a product in ZS given by a product of primes like this, then we define similarly the Kolyvagin derivative to be the product of this derivative. And now it will be an element in the group ring of delta n. Okay, so why do I define all these elements? So this is because we have the following result. First result is that, okay, you look at, maybe I just remind you, so you have this F, this is the Jn. So Jn is an extension of F, right? So I'm looking at things modulo T. So I look at this quotient, F cross over F cross to the T. And it turns out that this is the same as the quotient Jn cross over Jn cross to the T, and then you take delta n, sorry, this is not the right notation, delta n co-invariant of this quotient. It will be the same as this quotient. So I mean, if I don't have a quotient, right, if I just look at Jn cross and then I look at the delta n invariant of Jn cross, then that gives me Fn cross, because this is the Galois group of Jn over F, right? But then what I'm saying is that actually when you take this quotient by f cross over f cross to the z, you still get this invariant. So this is some Galois cohomology calculation that you can carry out. And the second thing that I want to tell you is that if I have an integer in this ZS1, zeta a primitive root, primitive nth root of unity, sorry. Also, rho is a primitive p to the nth root of unity, then the image of alpha rho zeta, right? So here, rho will be an element in F, zeta will be an element in Jn. So when I look at the product, that gives me an element in Jn. And then I apply alpha to this product, and then I hit this with this Cauliflagian derivative. And then I want to look at the image of this element in this quotient, right? I mean, a priori, this just gives me an element in Jn cross. This is a cyclotomic unit in this field. After I apply the Cauliflagian derivative and I look at the image of this element in this quotient, what you can show is that this is invariant under delta n. So in other words, once you look at this projection in this quotient, you can identify this element as an element in this quotient instead. So you start off with something in an extension, and then you get something in the quotient defined over F. So in other words, this cyclotomic unit applied to this Cauliflagian derivative gives an element in F cross over F cross T, and we would denote this I R alpha zeta. So here I'm fixing rho. So remember, rho is just some fixed primitive p to n root of unity inside F. So we'll fix rho from now on. And then as zeta vary, as n varies, then you get a bunch of elements in this quotient.
May I ask a question, please?
Yes, please.
In the definition of the product alpha, some of the exponents were half integers. Do you have hypotheses that make sure that in all alpha is a rational function?
Yeah, I guess I'm assuming everything is co-prime to 2. So like when I look at this roots of unity, it makes sense to talk about the square root, because like if I'm looking at 2 modulo an odd integer, then 2 is invertible, and so I can find an inverse of 2. So.
Oh, okay. So you take the square root within that field.
Exactly. Okay, so yeah, I mean, like we already saw this 2, I guess, yesterday, right? Like when we look at these cyclotomic units, yeah, I already have these 2 here. So, anyway, so we have this, and then yeah, sorry, I keep going forth and back. Yeah, so okay, so now I have this set of elements in this quotient, and so the point is that by lemma 1.8, it tells me that these elements are somehow comparable in a certain way. So it tells us that if, let's say if I have elements which is n root of unity, and I write zeta as a product, let's say, n is the product of qi, and then uqi is some qi root of unity. Okay, so what the lemma 1.8 tells me is that, well, when I look at the element I get from zeta, which is given by this product, then this is somehow compatible in a precise sense with, say, I divide this by one of these units. Okay, so the norm relation tells me that I have some set of elements in this quotient that are that satisfy some kind of norm relation. And now I have to wave my hands a little bit and say that by Shepard-Tariff argument, you can find this qi that gives you some nice property. So Q1 up to QR. Sorry. And then we get this. So I can find some set of appropriate primes such that when I apply this R alpha to these units, this root of unity, the result that I get in this quotient gives me some nice property. So I'll just tell you what the properties are. So we get some R morphism, which I'll write as eta j, which will be some morphism on this module. So, sorry. Okay. So this module will be inside this F cross quotient by F cross T. We'll go into R. And let's say, so this, I'll send this to something that I'll call yj star for some yj in R, and sorry, no, not in R, in lambda, I think, and then this yj has some nice property as well. So yj will ionate this quotient, and we have furthermore sorry, so I'm sorry, yeah. So this, I think they should live in R. So I'm taking projection like this. Okay, yeah, okay. I mean, obviously, I mean, I'm not explaining how to get these properties because it requires a lot of work. But the point is that, so I'm getting this set of morphisms thanks to these elements. And then these morphisms will give me some nice elements such that they are somehow compatible in some way. Like as you change J, you will get this generator Fj and also this delta in that you chosen in the beginning. And then also like the the point is that these properties together will give you the divisibility you want in theorem 1.7. Yeah, so the point is that together with all these properties, what you get is that so you just repeatedly apply this equation, and then you will get this inclusion, and then further from my double star, you also know that you have this inclusion. And so, if you combine these two equations, then you would get something like this. So this gives you the inductive step you want in the argument for the theorem 1.7. I mean, okay, so yeah, I apologize for all these technical details, but like I just wanted to tell you that the fact that these elements you get from your cyclotomic unit satisfy this norm relation will give you this inductive step where you can prove that theorem. And so this is like the only thing that I want to say. Like I don't want to like go into the technical details of this proof, but yeah, so I just want to show you like why we want to have this norm relation. And so this gives me, like I said, one inclusion of the main conjecture. So maybe I'll just say a few words how to get the other inclusion of the main conjecture. We can compare. So once you have one inclusion, you know that one power series divide the other, and then to show that they actually give you an equality, then we can compare leading terms via control theorems again. So yeah, so another message that I want to convey today is that like the control theorem is really useful in proving results in universal theory. So what happens is that you have two power series that tells you what happens for the whole extension. And now by the control theorem, you can go from the whole extension to like the ground field. And then on the ground field, you also have some relation between the two sides. And then so you can then compare what happens on the ground field, and then that tells you something about the leading coefficients of the power series. And then that allows you to conclude the equality of the main conjecture. So so I guess what I want to convey is really that, okay, so what is an Euler system is this kind of non-compatible element that should encode some kind of arithmetic information about the object that you are interested in. So now I want to move on to give you the definition of an Euler system. And a really good reference would be the book by Rubin, which is just called Euler system. So it's a very detailed and nice book to read. So before I give you the definition, I want to, first of all, go back to the cyclotomic units. So how to see cyclotomic units as an Euler system in this framework by Rubin. So consider the short exact sequence say. Yes, I'm not writing really well, so this is really Q cross bar, and then I can take Q zeta M, that Galois cohomology. That gives me a map. And then I take inverse limit as n varies, and that gives me a map from Q zeta M cross into H1 Q zeta M ZP1, right? So ZP1 is really just the inverse limit of mu Pn if you want, or you can think of it as this set of ZP equipped with the cyclotomic character as the Galois action. So in other words, remember my cyclotomic units are elements in this field, and so what I want to say is that the cyclotomic units are, you can think of them as cohomology classes via the Kuma map. Right, so, and these cohomology classes will satisfy some non-relation, as we have seen. So the general definition of an Euler system is a bit like that. So they are cohomology classes that satisfy some non-relation. So now I want to tell you the formal definition of an Euler system. So T, I fix T to be a finally generated free ZP module equipped with a continuous GQ action. All right, V to be T tensor by QP. W will be the quotient of V over T. T star will be the linear draw of T into ZP. V star will be similarly the linear draw of V to QP, and then I write W star to be V star over T star. And I'll define this polynomial PQX V, so Q will be a prime here. It is given by the determinant of 1 minus x sigma q minus 1 v I q. So I believe you have seen this maybe in one of the lectures earlier about I forgot which one, sorry. Was it the one about Beilinson-Flach Kato conjecture? So yeah, so you have the L function, which will be given by this product. Okay, and then so I will fix a set of primes to be set of primes such that it is the ramified primes together with the prime P. So here IQ is the inertial group. So when VIQ is not V, then we say that the Galois action is ramified there. And I assume this set is finite. Okay, so now having fixed all this notation, then I can tell you what is an Euler system for this representation. An Euler system for T is a collection of classes which will be denoted by CM for the time being. So it would be classes like this, where M will be N times P to the R, and N is a square-free product of primes, which is not in sigma. Okay. Okay. So also we want these classes to satisfy some norm relation. So the norm relation is given by this. So when you go from a class defined over Q zeta ML to Q zeta M, if my L divides this M, I want to get back CM. Otherwise, if L does not divide M, I need to modify this by some Euler factor. So this is why we call an Euler system, because of this Euler factor. And there's some, yeah, so let me just write this down. Right, so this norm relation will give you precisely the relation we saw for Euler systems, for cyclotomic units earlier. So let me just illustrate this. So when T is at P1, which is the representation we saw earlier. In this case, the only prime that ramifies is P. So V will be QP1 and then V star 1. So V star 1 is here. So V star 1 will become just QP. And then like the Euler factor that you have here will be what? So it would be, you can work this out because the action is just trivial. Then it's just given by 1 minus x, this polynomial. So when you plug in this sigma L minus 1, this is precisely the factor we saw when we were studying cyclotomic units. So we have precisely this. Okay. Okay, so this is the definition. So one thing we use Euler systems for general representation is to study summer groups. So again, I believe you have saw the definition of a summer group. Perhaps I'm not entirely sure because I didn't watch the lectures in entirely because it was pretty late for me. So, but anyway, so I'll just tell you about this. So if K is a number field, so we will look at this summer group S P K W. So now I'm looking at the general setting, not this example. Sorry. So S P K W will be this kernel. So there's some unramified subgroup that I will give you the precise definition. And so the summer group that I will be looking at is the one where when I localize at P, I get 0. And And let me write Q cyclotomic could be the cyclotomic ZP extension of Q. And then I will write the summer group of Q sec W to be the direct limit of all these summer groups inside Q sec, because I only tell you how to define the summer group for a finite extension, whereas Q sec is an infinite extension. So I take this direct limit, and then I let Y infinity to be the dual of this summer group. Then, so I use this notation on purpose. We have seen a Y infinity before, and I'm using the same notation here. And also I will write, so this is a lambda module. So my lambda is slightly different now. So this is a lambda module where lambda is the Iwasawa algebra for the cyclotomic extension, which is slightly different from the one we saw earlier. So the point is that using this Euler system, there's a theorem which tells you that you can bound this summer group using the Euler system, if there's one. Okay, so so this is a result due to Kato Ruben, and also there is some work by Perrin which tells you that, well, under certain, sorry, not writing really well. This is still pretty early for me. Sorry. Certain hypothesis, which I won't be precise about today. If we have an Euler system, if let C to be the image of this Euler system in I'll call H1 Iwasawa K infinity T, which is simply the inverse limit of H1 Kn T. So what is Kn? I didn't tell you, but like so. Oh wait, sorry, I didn't. No, that's not this. This should be Q sec. So we have Q sec, and then Kn is some finite extension inside. So this is when you have a cyclotomic extension. The Galois group of Q sec over Q is isomorphic to ZP, and then I can find a sub-extension where the Galois group is Z modulo P to the N. So the fact that this Euler system satisfy this norm relation will allow me to build out an element inside this inverse limit. When you take the, so this inverse limit is taken with respect to the co-restriction map. And so the fact that these classes satisfy this norm relation will give me an element inside this inverse limit. And I assume that this image is not inside the torsion part. So this is a lambda module, so I want to make sure that it is not inside the lambda torsion part of this module. So if you have this, then you can show that this y infinity, which was the Cauchy eigendual of the summer group over Q6, this will be a lambda torsion module. And you have the following divisibility. The characteristic ideal of this module, it will divide, divides the index of C. So what is this? Is the ideal generated by the following. Okay, so yeah, it is a bit more complicated than what we have seen earlier for cyclotomic units. But the point is that the idea of this theorem is somehow inspired by what we can do with cyclotomic units. The fact that you have these classes that have this norm relation, you can then again apply these Kolyvagin derivative to these classes, and then you can then build up all these homomorphisms, and then you can then use them to bound this summer group, a bit like what we have seen before. So obviously I won't give you the details of this proof, but yeah, so I just wanted to tell you what you can do with an Euler system for a more general representation. And so this is the general setting. So I want to maybe give you some feeling of what we can do in another more concrete example is when you look at elliptic curves and modular forms. Because this is quite abstract and maybe too general. So like we can maybe look at another setting where you do have an explicit Euler system and how it works in action. So for this, a good reference would be Cato's paper called Piedic-Hodge Theory and Values of zeta functions of modular forms. So in this particular setting, I have something more explicit. So let's say we just take an elliptic curve, and I assume the elliptic curve is good ordinary at P. So this would be an elliptic curve over Q. And I assume it has good ordinary reduction at my fixed prime P. And T, in this case, I'll just take T to be the Tate module. So I do have a Galois representation. And so we have a parent rule map, which is, let me denote it by a co-EP. So this is the local version of the cyclotomic extension. So this is the cyclotomic ZP extension of QP. Okay, so this is a bit like the Coleman map we saw in theorem 1.4. So where we were looking at just some local units in some cyclotomic extension, and then we can convert these local units to some power series. So parent rule showed that you can do something similar for cohomology classes. And then it turns out that you have a similar exact sequence like the one we saw earlier. We have an exact sequence which looks like this. So I don't know whether you remember the earlier exact sequence. We have an x infinity here. We have a y infinity here. So here I still have the y infinity that I defined earlier for the more general representation. And this is like the classical summer group that you may be more familiar with. And then you have these terms here. And then we have a special element which I would call CBK, stand for Beilinson-Flach element. Then it forms part of a Euler system. And then the point is that when you look at this Euler system, when you apply the Kalman map to these classes, you get the p-adic L function for E at P. So it's a bit similar to what we saw earlier for cyclotomic units, where you apply the Kalman maps to the cyclotomic units, you get the Kuperter-Leopold p-adic L function. So here you get another p-adic L function. And then the point is that you will get something like this, roughly. So it's really similar to what we saw earlier. And so the using an Euler system argument, then a bit similar to the one we saw, we will then get you get one inclusion of the main conjecture, and so the main conjecture would relate the characteristic ideal of this module to this module, which is equivalent to the which would be equivalent to saying that the characteristic ideal of this module is equal to this module. So what you can prove is that LEP will be inside the characteristic ideal of the summer group, like this. Yeah, so I think I'm running out of time, so I'll stop here. So in my last lecture, I want to move on to say a few words how these elements are constructed in this setting. And then I will move on to say something about Beilinson-Flach elements and how they are used in more general setting where you have tensor product of representations coming from two modular forms. So thank you.
Any other questions? Okay, if not, let's thank Antonio again.